Welcome everyone to once again join me in this exciting journey into the deep end of Targetable, a fast and reliable database for financial transactions. So let's get started. For the past 5 episodes or so, we've been through a slow slog through repairing protocol of Targetable. As a reminder, Targetable includes a storage fault model. Targetable assumes that if it writes something to disk, that data might actually get corrupted, and when it tries to read the data later, the data might not be there. So it includes specific code to take advantage of cluster redundancy to repair local state. So if a replica saves prepare, then crashes, then restarts, and realizes that prepare isn't there, it repairs this missing prepare from other replicas. And the core idea here is that actually let me start drawing stuff here. The core idea for a prepare is that each prepare actually is first of all like 1 megabyte of payload. So this is like payload and this is big, but on top of payload there is header, which is small, like 256 bytes, I think. I think it's even smaller. Well, let's take a look. I don't remember what is the size of our header, which I probably should remember. So okay, let's go to message header. Here is the header, and as usual for any data structure, we have a size of header is 1/4 of a kilobyte. So yeah, we have a small header. Then we have 26 bytes. Then we have a large body, 1 meg. Oh, 1 meg. 1 meg is the total, so 1 meg minus header. And this thing here, crucially, includes a checksum which covers this entire body. Then The idea is that bodies of prepares are generally on disk, and when you need to use a body, you usually go to disk and read it from disk, while headers are kept in memory, so that when you repair the headers, when you repair prepares, the algorithm is that you first repair headers, and then with the header, you know the checksum, so you could provably check that if you repair prepare and someone sends you a body, that the body is indeed correct. So kind of like you start with a checksum and then go from there. Additionally, not only the header covers, the header's checksum covers everybody, it actually covers, transitively covers bodies of all the previous headers, because each header also includes parent checksum. And that thing like points over here. And so you see kind of like this, there's like this interlocked hash chaining thingy going on with some poorly drawn arrows. Okay, so basic idea is that you got headers and you got bodies. Today we are going to discuss DoViewChange, which is like the core of the consensus algorithm. So let me kind of like speed run the overall normal operation of consensus. So there is a primary, and primary prepares. So it's like 3 prepares with like different ops. Let's say this is like op 90. I don't need this one. So this is also prepare. Okay. These prepares are then sent to backups. So prepare is going to get sent to the backup of the network. And once backup receives this prepare and durably stores it on disk, it acknowledges this fact by sending crazy arrows here, by sending a short header only prepare OK. So when the primary receives prepare OK from backup, it is a proof that this data is now stored durably on disk. So there is a question in chat whether I like Zig or Rust better. Well, let me answer this way. One question you should never ask your kid is whether they like mother or father more, because, well, if they start actually thinking about this question, they might come to some reasonable conclusion. So I wouldn't say that like I love Zig or Rust more. Like I love both those languages. It's like brilliant languages, and it's important to realize what is the difference between the two, and which contexts make more sense for Rust, and which contexts make more sense for Zig. And for Tagabital, for our particular use case, Zig ends up being a better choice, at least as far as I think so. So anyway, that was a tangent about Rust versus Zig. And now let's get back to consensus. Okay, so once the primary accumulated a quorum of prepare OKs, it actually goes and marks a particular prepare as committed. Also, a preparer keys obviously carry the op number. So once primary receives a quorum for this particular quorum of a preparer case for this particular op, this thing gets committed. Now, the cool thing about target middle is that this also actually happens concurrently. So the primary has a whole pipeline of prepares, and it might actually be the case that kind of like it receives a quorum for op 92 before it receives quorum for op 91, and in that case it first waits until 91 is confirmed as well. So this is kind of like normal operation when there is a primary, and it slowly builds a history. So you could imagine this as kind of like a linear history of prepares, which is built by the primary, and this is like nice and clear. And like this is like primary, so primary kind of like always have the whole sequence of prepares for a given view, because primary decides what gets into view. Backups actually might get like fragmented picture. So this is like, for example, backup 1. And this is backup 2. But if they kind of like together happen to cover like the whole picture, then a thing gets committed. So for example, for like, for any point here, it is covered by the primary and at least by one backup. So the primary gets preparer key for itself and also for one backup, and it considers message committed. Now, the interesting thing happens is if at some point some machine crashes or gets partitioned, and another primary picks up the work. So let's say here something bad happened, like a fire, and then another machine became a primary. And the thing is, like everything is distributed and asynchronous. There is like no a single place where we kind of like confidently say, hey, things are on fire now. Every machine might have a different view. So it could be the case that this blue primary actually continued a little bit more after this fire. And kind of like for some period of time, this blue and red primary actually functioned in parallel. And so, for example, we have like two versions of op 92. So we have view 3, op 92 here. And here we simultaneously have view 2. But what our DoViewChange protocol is going to guarantee is that if we have this kind of situation, then this op is guaranteed to never be committed. And like how typically consensus protocols solve this problem is that, well, they kind of like collect when you want to do a view change, when you want to change a primary, you kind of like ask a quorum of replicas what headers they have locally. Then from this quorum, you select kind of like the longest chain. And you say, hey, this longest chain is actually what is true. Because you have a guarantee because you are checking for quorum condition on preparer case that every preparer which actually acquired a quorum of preparer case should be on this longest chain. Because view change quorum and preparer key quorum intersect. Now, This is for like your classical consensus algorithm, which assumes that disk cannot fail. Unfortunately, failing disk might throw a wrench in the works. So let's work through one particular example. Let's say we have R1, R2, and R3 as our three replicas, where like the quorum is 2. And let's say that this one, R1, is currently a primary. And let's say that it has prepare, and it sent that prepare to R2, and R2 persisted this prepare to disk. So let's say that this is like prepare, persisted this to disk, and actually sent back prepare OK. Now, R1 crashes, so it loses like this information, and then restarts. And we end up in a situation where this prepare only exists on R2. And now, the worst bit. This prepare is on R2 on a hard drive. And then hard drive of R2 gets corrupted. So we have like this corruption here. We don't, like, there is like bit flip there, and we can no longer get this prepare. So this actually shouldn't be a problem, because what happened is that there is simply only a single copy of this prepare in the cluster. There was only ever one prepare OK for it. And that single copy got corrupted. And that's kind of like something we should survive, because, well, we assume the disk fails. But now, what happens during view change here? So now suppose that, like, again, something bad happens and we kind of like lose a primary and now like need to view change. So if R2 doesn't participate in this view change, which I cannot draw because I put them all into the same text box. Okay, let's say that this is a separate. Okay, so let's say that R2 doesn't. Okay, R2 like gets completely partitioned, and there is like view change only between R1 and R3. Well, this is okay. They don't get this message, so this message doesn't survive in the new view, and that's perfect. But what if R2 is a part of this new view change? Well, if R2 doesn't have a body for this message, but it still has a header for this message. So when it advertises during view change which prepare OK it sent, it says, hey, I have a SP here. I prepared this. And well, if you just pick the longest log to select which should be the new primary, then you should say that, hey, actually that P2 is like the latest prepare that was ever prepared. So we should include P2 into our new view. And this is a problem because, well, you decided that, hey, you want this to be a part of a new view, but this prepare is completely gone from the cluster. A single disk failure makes this prepare completely unavailable. And, well, like, you are now stuck. So you decided that, hey, this must be part of a view, but also this prepare simply like does not exist. This message doesn't exist, as the interesting story at the top of Lobsters says today. So yeah, we are stuck. We cannot do this, and this is actually kind of like interesting. Because it means that we actually need to patch our consensus algorithm to like take advantage of it. And what is the core issue here? Well, the core issue here is that if at least one replica saw a prepare, we kind of like decided, hey, this thing happened and it should be included in the view. But this is fragile, because if something is only ever seen by one replica, then if that one copy gets corrupted, the game over. Like, you decided that it must be a part of your hash chain, but you don't have a body, so like the cluster is completely stuck. So how do we get out of this bind? And the idea here is control or the NAG protocol from the protocol-aware recovery paper, which is kind of like the core paper, which Rust Analyzer Target. I need to stop confusing Rust Analyzer and Target. The core paper on which Target is built up. Again, as usual, like every time I describe any aspect of Target, I say, hey, this is the core aspect of Target. Oh, because it is true. Like, Target has many brilliant ideas. Anyway. Control protocol on the NAG, also known as a NAG protocol, and this is from protocol aware recovery awesome paper. Okay, so what is the idea here? Well, the idea here is that, okay, so let's say we have this picture where R2 participates in this view change. But we can ask R1 and R3 whether they saw this prepare, whether they have ever sent prepare OK. And R1 and R3 would actually say, hey, we haven't seen this prepare. So what you get is that you have one replica which said, hey, I sent prepare OK here. But you also have two replicas which said, hey, I have never sent prepare OK for this message. And this actually allows you to conclude that this message could not have been committed. So you could actually go and truncate this message out of the log, because you can positively reason that it could not have been committed, or kind of like unwinding this back. If we assume infallible disk, then our consensus algorithm can be very optimistic. If something exists somewhere, we take it. If we assume that disk fails, we need to make sure that we don't take information which wasn't sufficiently replicated and which might get corrupted. So then you need to have a positive proof that, hey, this didn't happen. Okay, hey, someone says that Larissa and Target stream happen at the same time. Well, if Larissa's stream is always at 5 p.m. UTC, I'll be willing to move mine, so no problem here. But that's a very good observation. Thank you, Embedded Boy, for pointing this out. Anyway, let's actually then look at how this is handled in the code. So the overall plan is that when replicas want to change a primary, they send DoViewChange message. DoViewChange message includes headers which a replica has locally. And it also includes kind of like anti-headers. For things which replica doesn't have locally, it positively says, hey, I don't have this thing. Then the primary collects a quorum of DoViewChange messages and looks at every operation, whether it is present or not, or sufficiently nagged. And that way it either decides which operations survive into the new view and which get truncated. So let's stop drawing and dive right into the code. But before that, give me 5 minutes to refill my cup of tea, because this is my third call today and I feel I need a little refresher. Okay, we are back. I have my cup of tea and I'm ready to continue. Let's start looking at the code. And before we dive into DoViewChange message, which explain how view change actually happens, let's look at start view. So what is start view? After view change happens and primary selects which headers survive into view for which the primary is, well, the new primary, it sends a start view message. So start view is a proof positive that this particular view has started and that the headers which are which are in the body of this start view message are part of the start view, and conversely, that the headers which are not part of the start view are truncated from this view. So when the primary, when a backup receives a start view, one thing it does is that it view durable update. Where it happens. Addition to normal from view change. Yeah. When backup receives a start view and transitions to this new view, what it does is that it also stores which view it has started. So each replica has a view which is kind of like the current view that the replica is in or tries to start, and the log view. The log view is the latest view for which replica received start view message. So kind of like your log view might be 10 and your view might be 20. And that means that between 10 and 20, you are trying to change view, trying to select new primary, and you weren't very successful then. So okay, that's start view. And the start view contains the messages which are parts of this new view. Then we have DoViewChange. DoViewChange contains view, which is, hey, we are trying to switch to this view. It also contains log view, which again says that, hey, I as a replica received, the latest start view message I received as a replica was for this view. And then it contains a bunch of prepares which I as a replica had. And here we should go back to, if you recall, we have in general kind of like this picture where, why it always resets? I always want to draw several lines at the same time, where each replica has partial view of prepare. So that's that is the headers and gaps in the headers which are included in DoViewChange. Another crucial thing which is included in DoViewChange is this NAC bitset, which says, hey, this is, I haven't received this particular prepare. So let's see how this is set up. NACs set. Okay. So this is send DoViewChange method. When a replica feels like it should change to a different primary, it sends its own set of headers. Interesting thing here is how we calculate this bitset of NACs. So we take all the headers which we have locally, and why this is in a view headers array, I'm not going to explain today. We'll probably look at updating of view headers like later, but let's say that's just kind of like that's the messages are like the headers we have like locally for this view, which might be incomplete because we are backup, so we might have a gap. And for each header, we decide where we actually have this prepare and whether we nacked it. And like important thing, nack doesn't mean that you don't have this prepare. Nack means that you have not sent prepare OK for this message. And it might be the case where you actually have prepare, but you can guarantee that you haven't sent an OK yet. So let's take a look here. For each header we have, we look our corresponding header from the journal, so what we should have on disk in memory. And we check whether this header is faulty, meaning that the prepare corresponding to this header is corrupted, or whether it is like dirty. And dirty means that we have a header, but we don't have prepare yet. So we decided that we want to write something, but we haven't yet written this. So now let's take a look at the cases here. This one is kind of like pretty interesting. So it says that hey, we want to have prepare on disk which corresponds to the header which we are going to include into a DoViewChange message. So because like the header is the same, but the header is dirty and not faulty. This is exactly the case which I was talking about. This happens when you, as a replica, you have just received prepare. You started writing into disk, but you know that you haven't finished writing into disk yet. In this case, you can be sure that you haven't sent prepare OK yet, because well, you are still writing stuff to disk. So you set this nack bit as true. The second case, our header in the journal is actually different. So when can it happen that like this header from view headers is different from journal header? Well, let's say you're a replica and you like participated in view 6, and then you received a start view for view 7, and in view 6 you accepted op number 90, but when you receive a start view for view 7, you actually realize that op 90 that you have received was truncated, and there is a different op for view 90. So in this case, you kind of like save that header from start view for view 7 in view headers, and you say, hey, this is the header that should be there, but your local header in the journal is truncated header from the previous view. And if that is the case, you haven't replied with prepare OK to that new correct prepare, so you also have a nack. Finally, it might be the case that that slot in the journal is simply blank yet. You haven't written anything in that slot yet, and in that case, you also can signal that hey, this is a not acknowledged. I don't have this header. Finally, we need to figure out whether we have this prepare, and this is kind of like that is the fun thing. Nack and present are not like the opposite. So it can be the case that you not acknowledge a prepare, but you still have it. Because nack is about prepare OK, and present is about prepare. And it might be the case that you have prepare, but you can guarantee that you haven't sent prepare OK yet. So when we can send a present bit? Well, the first case is that if we believe that this prepare is available on disk. I think we should also check that is not faulty, because if it is faulty, it's actually not present. Well, actually, I think we might not need to do this, because I think prepare checksums for faulty would actually store like blank checksum, but well, this is something to recheck. Anyway, so we have this on disk, or we have this in memory because we like writing this to disk, or we have this in our pipeline cache, which I haven't discussed at all, but well, Hopefully someday we'll get to pipeline cache. Anyway, so kind of like we have this prepared one way or another. After that, we create our DoViewChange message. So these are kind of like boring things, boring standard fields. Then we set our log view, because again, log view is when we've last received start view. Then we include like now a NAC bit set and present bit set, and finally we go and set the body of this message to the headers. We've just included the checksum. Again, like two checksums. One checksum covers the body, and then the checksum which covers the checksum which covers the body. So that when we receive a message from the network, we don't need to receive the whole message to verify the checksum. We can receive just the header, verify the header, and then we receive the body, so that the size, so that we can trust the size in the header. Okay, and then we like send the message. Okay, that's kind of like the sending part of DoViewChange protocol. Now let's look at the receiving part. And that is function quorum headers. So this is different. This is like receiving side. Now we are a prospective primary, and we have collected a view change quorum of a DoViewChange messages. So you see, for each replica, we have an optional DoViewChange message, and there should be some assert that we have like most of them, and enough of them not known. But anyway, let's see. So we have like this bunch of messages, and we need to decide what we are doing with that. Is this enough messages to like truncate or survive all the headers into the next view? So let's just go and look into this code. Okay, there are like some trivial assertions on the quorum conditions here, and well, we'll discuss quorum conditions separately, because quorum conditions are actually quite interesting here. They're not like, you know, quorum conditions you read in the Paxos paper. There is a twist here. Okay. Okay. Yeah. This is it. So first of all, we kind of like we take this. This is like, well, this is kind of like slightly boring accidental complexity, where we take a message for each replica, which might be not null, and we instead return a bounded array only of non-null messages. So DVC array is, as you can see, just a bounded array. So array which is located on the stack. Okay, and if we haven't got the quorum of ViewChange quorum of messages, if we don't have an intersection property, we say to the caller, "Hey, caller, we are awaiting quorum, so we can't progress yet." Otherwise, we pick canonical messages. And what the hell canonical messages is? And well, I'm going to explain it, but you aren't gonna like it. So remember the last lecture of the last year, where we discussed mathematics of consensus. And there, like, we had this kind of like property that primary collects votes from the quorum of backups, and among these votes, it kind of like selects the vote from the highest ballot. And like that vote from the highest ballot defines which value is safe to choose in the current ballot. So that is the thing. This is what canonical is. So remember that we, like, each DVC carries with itself a log view. A view when the replica received start view message. So among all those log views, we select like the highest one. And messages with the highest log view are called canonical. Yeah, so what is like the physical sense of physical purpose of canonical messages. Okay, I've made myself a tea, but I forgot that I could actually drink it. Sorry. Okay, what is the purpose of canonical messages? Well, canonical messages tell us like the latest history of a cluster. We kind of like, due to the quorum conditions, we know that canonical messages contain information about the latest view change that have happened. So if we if we look at the canonical messages, we cannot miss anything. So okay, we take this set of canonical messages. Now, what do we do with them? Well, first of all, we define the highest op among these canonical messages. So kind of like you might have like in view 2, you might have like the highest op equal like 92. But then in view 3, you actually truncated 92 and there is only 90. So if view 3 is canonical, you say that op head max is 90. Because view 3 is higher than view 2, and if you know that in view 3 the op is only 90, then you also know that the primary, which started view 3, truncated op 92. So locally, there might not be enough information to truncate 92, but you trust that the primary who laid the log view didn't mess up, and if it truncated 92, that it should have been truncated. Okay. And then we, let's look at the implementation of op max canonical, which should be relatively straightforward. It's actually interesting because I wonder if those two functions should better just, take the DVC array right here. But anyway, because like here we compute canonical here, and here we compute it again, but never mind. So, we take messages, look at canonical ones, and write a simple loop to detect the highest message there. Okay, so op head min, it's okay. So this is kind of like op head max is like the highest messages which could survive in the next view. We might still truncate it, but we have a guarantee that nothing higher could be a part of our view. That is kind of like the upper bound on what we as a primary need to decide on. Op head min is the lower bound. We know that everything below op head min is guaranteed to be committed. And we compute that as just compute that by just looking at commit max of each DVC message. So each replica sends to us what it thinks is the latest committed message, and then we just pick the maximum of that, which should be relatively straightforward. Again, so we for each DVC, we look at the headers in this DVC. We look at the latest op. And again, because we have this constraint that there is at most pipeline ops in flight, then if we have op, we know that op minus pipeline length is like guaranteed to be committed. And then we actually look, it actually feels, it feels strange. Like why can't we just include commit max into a DVC? Because I think we've like skipped that before, because before our headers were only wide 128, but now we have more space there and we could just include commit marks right in here because, well, like the standard replica should communicate with commit marks. But anyway, here we kind of accept. Here we can derive it. So now, kind of like between this ophead min and ophead max is something we, as a new primary, should make a decision on. So we could either take these headers or we should truncate it. And the logic here is that everything which could have had a quorum of prepare OKs, we should take. And everything which is guaranteed to never had a prepare OK quorum, we can truncate. So let's take a look here. Well, first of all, we for each op. Oh, yeah, and important thing. So we have like a bunch of a whole pipeline of outstanding ops, which actually makes me think that we should assert that ophead max minus ophead min should be I'll just called constant stan pipeline count max or something. Yeah, basically, I think this should be true. Anyway, so we have like a bunch of ops outstanding. And the thing is, if we truncate some op in the middle, then we can truncate everything on top of it as well. So that's why we start from the lowest op. And the first one we truncate is kind of like benefit because we don't even need to consider everything's built on top because we do commit in order, and if a single op is truncated, if a single op is guaranteed to not be committed, then everything on top of it also guaranteed to not be committed. Okay, so first of all, we see if we have canonical header for this op, which is like simple. We just iterate through all the canonical DVCs, and we check if it has this message with this particular op. Okay. Then we need to figure out whether we have a header. Now we need to figure out whether anyone in the cluster has a copy of this header, so they think that they have this prepare on dictation is not corrupted, or whether enough of cluster members actually knock this header and it can be truncated. So let's iterate through all of the DVCs. If the latest op in the DVC is smaller than the op we are currently considering, then that's clearly a knock. This replica clearly doesn't have this, didn't send a prepare OK for this header. Okay, that's a knock, that's easy. Otherwise, if this op is too late for the DVC, it's not in there, then okay, it's also a knock because otherwise replica should have included this. Otherwise, yeah, we should see what replica has for that op. Okay, so if this replica actually has this header and replica said that it has this prepare, and also this header actually matches the header from canonical log view, then we have a copy. This is kind of like a happy path. So someone knows about this header. Otherwise, if this op is explicitly knocked, then this is a knock, and we can count this as a knock. Otherwise, like the fun case, this DVC includes this header, but we know that this is different header from the header we have on a canonical DVC. So we know that this header was actually truncated in some later view. Then again, this op is also null because the replica has a different header there. So okay, if we collected enough NACs, then we can truncate this op and say, hey, this like the previous op is the true head of a new view. Otherwise, if we don't have NACs and we don't have any copies, then we are in the case where this op might need to be in the new view, but we cannot repair it. Like we need to wait for more messages until we can either truncate it or until we can repair it. So we like return either await and repair if we haven't received messages from all replicas, or if we have received messages from anybody and nobody has this header, then we say that, hey, we are stuck, which might be the case. Again, we guaranteed to stay live unless there are only so many faults on disk, and in the unlikely event that the prepare is corrupted on every single replica, we will remain available, which is correct behavior. Okay. Otherwise, this op is not nacked and it is present in the cluster. It has at least one copy, so we need to continue looking for the next op. And that sort of kind of like completes this view change protocol, because if we successfully identified a head here through truncation, or if we find out that every header we have in a canonical log view has a copy, well, we know that, hey, this is the true head of the new view. And that, I think, is more or less everything I wanted to cover today. Again, this is kind of like hand-wavy, and like there are like a lot of finer details to like fully appreciate and understand this algorithm, especially around like log view and view. But this should give you like the rough idea. And again, the idea is that when replicas want to change view, they collect all the headers they have locally and send those headers as a DoViewChange message to the replica, which should become primary in the next view. This prospective primary collects DVCs, DoViewChange messages, from all peers. And looking at this set of messages, it needs to determine the head of the view which it is about to start. And how you kind of like detect the head? Well, naive algorithm picks just the highest op number from a canonical log view. And this is how like almost every consensus protocol out there works. This naive algorithm is vulnerable to disk failures. Because a message which was not replicated to a quorum of replicas could get corrupted on a single replica, and that kills your consensus. So that's why we do slightly finer grained iteration. For like, we look at all the ops from the canonical log view, and for each op we check whether it can be truncated, whether it has enough negative OCs to guarantee that there wasn't a quorum of OCs. And if that is the case, we then go and truncate this op from the view and say, hey, actually the previous one is the true head. And I think that basically covers it. What I didn't cover today is like how we actually get into this quorum headers function. Like what, when replicas decide to like do view change things. And also I kind of like hand waved around how replicas include like their view headers. Like I said, hey, there is a self view headers array, which I'm not going to talk about, and I'm not going to talk about it. So this is, I think, what we're going to look at next time, next Friday at 5 p.m. UTC, unless I move it to avoid the clash with Laris. We will look at the actual control flow, how replicas get to initiate this view change process. Okay, let me catch up with the chat here, because there is a bunch of stuff here. Okay, there's like some interesting discussion about like functional programming in Zig, but no direct questions. But kind of like, yeah, generally kind of like if you like functional programming, you're not going to like Zig. Like you would hate Zig, because it's kind of like I wouldn't say that it's like anti-functional, but it is anti-functional. Like it is like pretty much like imperative way. And again, this is not to say that again functional programming is better and imperative programming is better. Like everything has its own costs and benefits, and everything is a right solution in some context. But for the kind of code we write here at Tagabitl, for the kind of like complex code which solves complex problems, actually these like very simple, straightforward imperative, let's do this and then that, and like there is no lambdas, no kind of like complicated control flow, just like simple for loop. And this actually is better. Like I mean, this is just again simple. Systems programming is simple. Simple programming needs simple solutions, and that's why kind of like Zig is a good fit in this context. Okay, this is a miracle. I haven't exceeded my 1 hour quota, so see you at 5 p.m. UTC next week, and thank you for watching.